KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
Free bus for LKG to 8th standard.
Free, hygienic and nutritious food.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class we are going to discuss displacement of a body executing simple harmonic motion. Displacement of a body executing simple harmonic motion, right? And after completion of the discussion, we will discuss one example problem related to this topic. Okay, right? See here, ma. So we already discussed in our previous class, right? In our previous class, we discussed what is a simple, what is oscillatory motion and what is periodic motion. What is the difference between oscillatory motion and periodic motion? After that, what is the difference between oscillatory motion and vibratory motion, right? And there itself, what is the definition of time period and what is the definition of frequency? And after that, we discussed one example problem that is related to the human heart. Average of a human heart regarding the heartbeat, that is, you know very well, 75 times in a minute. There itself we expressed that value. Based on that value, we found what is the beat frequency. That's we got it as 1.25 Hz. And then what is the time period? That's we got it as 0.8 seconds, right? Okay. So basically, in our previous class we discussed oscillatory motion, periodic motion, oscillation, vibration, time period, frequency, and one example problem, right? Okay. Next, displacement. Next one is displacement, right? See, first of all, we are going to discuss what is displacement in case of oscillatory motion. In case of oscillatory motion. In case of translatory motion, we already discussed, you know, in case of that is motion in a straight line, right? We discussed what is the displacement in case of translatory motion. Okay, right. Now, in section, that is what previous section, right? Here, we define displacement of a particle as the change in position vector, right? We define displacement of a particle as the change in position vector. This is what the definition of displacement in case of translatory motion. In case of translatory motion. But in this chapter, we use the term displacement in a more general sense. In this chapter, we use the term displacement in a more general sense. So how we means, you know, it refers to change. It refers to change with the time of any physical property. It refers to change with time of any physical property under consideration. Right? Okay. And for example, if you see that rectilinear motion, right? If you see the rectilinear motion, a steel ball on a surface, the distance from the starting point as a function of time, is its position displacement. You know, what is the choice of the origin? Choice of the origin is a matter of convenience. Otherwise, if you take a block attached to spring, you know, the other end of which is fixed to a rigid wall, and the other end, see, two ends are there, no? So one end is fixed to the rigid part, that is to the wall, and other end we are going to make it to displace, right? So generally you see here like this, right? See, this is the end which is fixed to the wall, and this end is free now, so you can make it to move like this and like this just by applying certain amount of force, right? A block attached to a spring, right? The other end of which is fixed to a rigid wall. Generally it is convenient to measure. Generally it is convenient to measure displacement of the body from its equilibrium position. Generally it is convenient to measure displacement of the body. It is convenient to measure displacement of the body from its equilibrium position. See, this is the equilibrium position. For example, you are going to displace it from here to somewhere and you are going to live there. Then what will happen? It comes back and goes there. So it is what? To and fro motion. So which is what you can say that oscillatory motion of a block, B-L-O-C-K, block. Right. For an oscillating simple pendulum, the angle from the vertical as a function of time may be regarded as a displacement variable. For example, you take this now. This is what simple pendulum now. So you are taking the ball, and which is first basically it is here. This is what equilibrium position, and now you are going to apply certain amount of force here. So this will move from here to there. Then what will happen? So this ball is going to move from here to there continuously, right? In this manner. Okay, that is. So the angle from the vertical as a function of time may be regarded as a displacement variable, right? That is. You know, the term displacement is not always to be referred. The term displacement is not always to be referred, okay, in the context of position only. Because here I request you to compare the definition of displacement and the situation to define displacement in case of translatory motion and in case of oscillatory motion. In case of translatory motion, we define the displacement based on the change in position. But here in case of oscillatory motion, we are talking the change in position with respect to time. That is what the main important difference regarding the displacement in translatory motion and regarding the displacement in oscillatory motion we have to notice. You have to notice, right? That is, suppose if you see this block, you know, this is what a block attached to a spring, the other end of which is fixed to a rigid wall, and this side the block moves on a frictionless surface. This is the frictionless surface. The motion of the block can be described. The motion of the block can be described in terms of its distance. The motion of the block can be described in terms of its distance or displacement x. Distance or displacement x from the wall. Okay, right. So this is what you can measure from the wall. Right. Now, and if you see this picture, this is what an oscillating simple pendulum. This is right. So its motion can be described in terms of angular displacement theta from the vertical. Its motion can be described in terms of angular displacement. This is the angular displacement. This is the angular displacement, angular displacement theta from the wall. Okay, right. So here we have two examples to discuss oscillatory motion, and more than that, to discuss the displacement of a body executing oscillatory motion, right? That's why he is saying there can be many other kinds of displacement variables. See, the voltage across a capacitor changing with time in an AC circuit is also a displacement variable. Right? In the same way, pressure variations in time in the propagation of sound wave, the changing electric and magnetic fields in a light wave are examples of displacement in different contexts, okay, that is one thing. And you know, the displacement variable may take both positive and negative values, right? In experiments on oscillations, the displacement is measured for different times. In experiments on oscillations, right? So in our physics lab, you may notice that, right? Actually, we could not have this experiment, that is what simple pendulum. But once upon a time, we had this simple pendulum in our syllabus, right? In our practical syllabus, right? So anyhow, this is what the simple pendulum. Here you can say that the displacement variable may take both positive and negative values. In experiments on oscillations, the displacement is measured for different times. Okay, right? And now you see here, we are going to discuss the mathematical treatment of displacement in case of a body executing oscillatory motion, right? The displacement can be represented by a mathematical function of time. In case of periodic motion, this function is periodic in time. One of the simplest periodic functions is given by f of t is equal to a cos omega t. F of t is equal to a cos omega t. Right. This is what the simplest periodic function you can write. Okay. Next, in the argument of this function, omega t, omega is the angular frequency, t is the time. Omega t is increased by an integral multiple of 2 pi radians. The value of the function remains the same. The function f of t is then periodic and its time period is given by t is equal to 2 pi by omega. T is equal to 2 pi by omega, right? See here. If the argument of this function omega t is increased by, an integral multiple of 2 pi radians, the value of the function remains the same. The function f of t is then periodic and its period t is given by t is equal to 2 pi by omega. Thus, the function f of t is periodic. With the period capital T. F of small t is equal to f of small t plus capital T. The same result is obviously correct. If we consider a sine function. That is f of t is equal to a sine omega t. Further, a linear combination of sine and cosine functions. Like, see here, f of t is equal to a sin omega t plus b cos omega t. This is like equation. It's a number of the equation, 14.3c, right? Anyhow, this is the equation which consists of both sine function and cosine function. That is what a sin omega t plus b cos omega t, right? This function is also a periodic function. With the same time period capital T. Taking capital A is equal to d cos phi and capital B is equal to d sin phi. Capital A is equal to d cos phi and capital B is equal to d sin phi. And equation 14.3c, this is the equation. And this equation you can also write as f of t is equal to d sin omega t plus phi. Here d and phi are constant which are given by like this is what d is equal to square root of a square plus b square and phi is equal to tan inverse of b by a. Here in this situation at this moment, the great importance of periodic sine and cosine functions is due to the remarkable result proved by French mathematician. The great importance of periodic sine and cosine functions is due to the remarkable result proved by the French mathematician Jean-Baptiste, that is what Joseph Fourier, that is the period from 1768 to the 1830, right? So he has given the hard work given by the scientist. So what is the hard work? So the importance of periodic sine and cosine functions is due to the remarkable result proved by French mathematician Jean-Baptiste and Joseph Fourier. Okay, right. But here one of the important conclusion, that is any periodic function can be expressed as superposition of any periodic function can be expressed, right? You can see here, right? I will show you everything. That is what you can see here, right? That is what is the sine, what is the function in terms of sine and cosine, and then if it is also a periodic function with the same period t, and taking capital A is equal d cos phi and capital B is equal d sin phi, and this equation it can be written like this: f of t is equal d sin omega t plus phi. Here d and phi are constant, which are given by like d is equal to square root of a square plus b square, and phi is equal to tan inverse of b by a. Okay, and here the conclusion, the important conclusion is any periodic function can be expressed as a superposition of sine and cosine functions, of different time periods with suitable coefficients. Any periodic functions can be expressed as a superposition of sine and cosine functions of different time periods with suitable coefficients, Okay, right, that is. Next, X example, that is what continuation to this topic. We had one example problem now, that is example 14.2. Which of the following functions of time represent? See, they have given 4 functions. He is asking that which of the following functions of time represent A, periodic, non-periodic motion. Give the period for each case of periodic motion. A is the periodic, and he is asking which of the following functions of time represent A, periodic, and B, non-periodic motion. Give the period for each case of periodic motion. Give the time period for each case of periodic motion, right? So one is sin omega t plus cos omega t, 2 is sin omega t plus 2 cos 2 omega t plus sin 4 omega t. So it is what somewhat big function, sin omega t plus 2 cos 2 omega t, sin omega t plus cos omega t, that is one function, and second function is sin omega t plus cos 2 omega t plus sin 4 omega t is the second function, and third function is e power minus omega t is the third one, and last one is log omega t. So out of these 4 functions, which function is periodic and which function is non-periodic, he is asking, right? After that, he is also asking time period for each case of periodic motion. Okay, right. First we are taking this function. This is what periodic function. Sin omega t plus cos omega t is a periodic function. It can also be written like this. That is what root 2 sin omega t plus pi by 4 plus pi by 4. It can also be written like this. That is what root 2 sin omega t plus pi by 4. And now root 2 into sin omega t plus pi by 4 is equal to root 2 sin omega t plus pi by 4 plus 2 pi, because if you are writing 2 pi, you are getting the same thing, no? That's why. And that you can also write root 2 sin omega into t plus 2 pi by omega plus pi by 4, omega into t plus 2 pi by omega plus pi by 4, right? Plus pi by 4. Okay, right. This is what the periodic time of the function is 2 pi by omega. The periodic time of the function is 2 pi by omega, right? That's what you can say. Next, second one. This is the second function now. This we are going to check. This is an example of a periodic motion. This is an example of a periodic motion. It can be noted that each term represents a periodic function with a different angular frequency. Each term represents a periodic function with a different angular frequency. Since period is the least interval of time, after which a function repeats its value, sin omega t has a period t naught is equal to, sin omega t has a period t naught is equal to 2 pi by omega, cos 2 omega t has a period, pi by omega is equal to t naught by 2, and sin 4 omega t has a period 2 pi by 4 omega is equal to t naught by 4, right? That is. Next, the period of the first term is a multiple. Period of the first term is a multiple of the periods of the last two terms. The period of the first two terms is a multiple of the periods of the last two terms. So if you observe the terms, you can say this one. Therefore, the smallest interval of time after which, therefore, the smallest interval of time after which the sum of the three terms repeats is t naught, and thus, right? And thus, I didn't write here, but I am saying, and thus the sum is a periodic function with a period 2 pi by omega in case of this function, that is what, sin omega t plus 2 cos 2 omega t plus sin 4 omega t, right? Next, third one, e power minus omega t. It is not a periodic, right? Why? Because it decreases monotonically with increasing time. See, because here minus is there, and you can write it as 1 by e power omega t. The function e power minus omega t is not periodic. It decreases monotonically with increasing time and tends to 0 as t tends to infinity, and thus never repeats its value, okay? That is right. Next, fourth one, log omega t. The function log omega t increases monotonically with time t. That's why, therefore, it never repeats its value and is a non-periodic function. It may be noted that as t tends to infinity, log omega t diverges to infinity. It therefore cannot represent any kind of physical displacement. So out of these four functions, he is saying that this is the periodic function and this is also periodic motion, right? So this is also periodic motion, but third one and fourth one are not periodic. Those you can say that non-periodic. Non-periodic functions. Okay. In this class, we focus to discuss what is displacement. What is displacement, and afterwards, what about the displacement of a body executing simple harmonic motion? And here we have oscillatory motions of two particular. That is, one is a mass attached to the spring, another one is a bob attached to the string. Both are executing oscillatory motion. And here, what is the time period and what is the mathematical function, a trigonometric related function consisting of sine and cosine functions, right? So which is f of t is equal to a sin omega t plus b cos omega t. And afterwards, what is a and b? What is the relation between a, b and capital D, right? And what is the value of phi? That is tan inverse of b by a. After completion of this discussion, here one important conclusion is any periodic function can be expressed as a superposition of sine and cosine functions of different time periods with suitable coefficients. Okay, that is one thing. And next we started to discuss the continuation example problem. Right, there they have given 4 functions. Out of these 4 functions we concluded which are periodic and which are not periodic. These 2 are periodic functions, these 2 are not periodic functions, because of the situation what I already explained to you. Okay ma? Right. Thank you.